Hi, let us proceed with our discussions about the design of reinforced concrete pad footing, which is subjected to the axial loads only. In our previous videos, we talked about the process to determine a suitable size for the pad footing. This is calculated on the basis of the service load. Due to the prescriptive methods that we use in the design of the pad footing. The prescriptive method requires the estimations of the size of the foundations based on the serviceability limit state. With a given ultimate load, we will need to convert the ultimate load into the service load by dividing with the factor of safety of 1.4. Assuming that there is an additional 10% loads due to the self-weight of the pad footing, we estimate the required contact surface area of the pad footing. And then we try and error and decide the size of the pad footing so that the actual contact surface area it will be greater than what is required. Not only that, we will need to confirm that the soil bearing pressure due to the load does not exceed the soil bearing capacity where the pad footing is sitting on. In this case, the soil bearing capacity is 200 kN per meter square, and the pad footing is subjected to axial loads only. That means there is no influence in terms of the moment to the soil bearing pressure. You may use these equations. Take the service load, which is this, plus the self-weight, which is this, divided by the contact surface area, which is this. Make sure the soil bearing pressure does not exceed the soil bearing capacity. This step is very important as it determines the stability of the pad footing. You will need to make sure this passes before proceeding with the structural design. Otherwise, no matter how strong you design the pad footing, the foundations fail by settlement. This can jeopardize the stability of a structure. Once this is completed, our next step it will be going for the structural design. Again, based on the prescriptive methods, the structural design it will be based on the ultimate limit state. Therefore, we will need to redo this process using the same set of equations. Only that we need to calculate the soil bearing pressure at the ultimate limit state. We will use this calculated pressure for us to calculate the moment acting onto the pad footing. Based on the moment acquired, then we can determine the amount of reinforcement bar required. Therefore, let us look into the calculation process for the soil bearing pressure at the ultimate limit state. The ultimate axial load is given 1000 kN plus the self-weight of the pad footing 50 kN as calculated previously, divided by the contact surface area of the pad footing, which is calculated by multiplying the H and the B of the pad footing, which is 4 meters square. Since there is no moment acting onto the pad footing, this whole thing will be equals to 0. Then you will obtain a consistent bearing pressure of 250 kN per meter square throughout the pad footing. Next, you will need to determine this span here. We term it Z1 and the Y1, representing the distance from the column surface to the edge of the peg footing in the major and in the minor axis. Since the size of the column is not square, it is in fact 300 times 150. 300 it will be the major axis and 150 it will be the minor axis. That will give you different values of Z1 and Y1. With the wider column width, the Z1 here it will be slightly smaller. In order to calculate this Z1, you will take the width of the peg footing. We are talking about the major axis, minus the width of the column in the major axis, and then divided by 2. You can always sketch the diagram for you to work out the Z1 and Y1. Same thing, you want to calculate the Y1 here. Take the width of the peg footing in the minor axis minus the width of the column in the minor axis, and then divided by 2. As in this case, the peg footing is only subjected to the axial load. Therefore, don't get confused by this sketch here. The bearing pressure it will be the same throughout, which means that this is equals to 250, this one equals to 250, and also this one equals to 250. Same applies to the minor axis. Having the Z1 and Y1 calculated, now we can go with the calculations of the moment acting at the column surface. There will be 2 moments calculated, and then we can calculate the moment on the basis of the plane here, and then calculate the total moments acting onto the column surface. To do this, it is always a good practice for you to sketch the diagram, having the stresses clearly indicated. Now you want to calculate the moment here. First, we calculate the moment due to the plane stress. When the stress is equal throughout, that means you need to only calculate the rectangular area that gives you a force times the lever arm. The force is calculated by multiplying this 250 kN per meter square times the width here, Z1, which is at 50 mm. That gives you F2. And then you need to multiply the lever arm, where this F2 it will act at the centroid of the area. That gives you the lever arm equals to Z1 divided by 2. That gives you the lever arm here equals to Z1 divided by 2. Then you get the plane moment 90.3 kN per meter. You will do the same for the minor axis. First, you need to determine the force by taking the pressure 250 kN per meter square, multiply Y1, which is 925 mm. That gives you the force here, times the lever arm, which is this 925 divided by 2. Make sure they are of the right unit. If you calculate on the basis of the Newton and mm, make sure your calculations it will all be in the Newton and mm. Now if you calculate on the basis of kilonewton and meter, then you need to convert the mm into meter. You will see the minor axis having a greater moment. This is because of the smaller dimensions of the column in the minor axis. resulting a greater length of y1 here. That subsequently leads to the higher forces due to the soil bearing stress, as well as greater lever arm. As a result, you will have a greater moment in the minor axis. Now, the calculated moment here, it will be on the basis of the plane stress here. You will need to calculate the total moment. You may refer to this diagram here. The plane moment, you need to multiply with the width, which is b here, in order for you to get the total moment. You will need to be careful with the b. This may not be an issue if you are proposing a square footing, when your h and b's are the same. Sometimes, due to certain circumstances, square footing might not be the case. For example, when you have adjacent pad footing too closely arranged with each other in order to ensure sufficient working space, it might end up to be a rectangular section. There is no restriction that you must have a square footing when subjected to only axial load. Of course, normally we will go for the square footing. This doesn't restrict the rectangular footing for such applications. Now, in the case that you are using the rectangular sections, the B here, you need to be careful. If you are talking about the major axis, the B, it will be the width of the column in the minor axis, which is this one. Now, if you are talking about the minor axis, the B, it will be due to the major axis, which if you view from the minor axis, the B, it will be this one. So, if you observe the calculations, the total moment here, it will be calculated by having the moment here multiplies with the B, which is the minor axis. And then when you want to calculate the moment here, it will be the plane moment multiply with the H, which is the major axis. That gives you the design moment of 180.6 and 214 kilonewton meter for the major and the minor axis respectively. And then you will need to calculate the effective depth so that you can design the reinforcement. These are the formulas used to calculate the effective depth. The effective depth is calculated from the top surface of the foundations to the centroid of the reinforcement. In the major axis, the effective depth is calculated from the height of the foundations minus the nominal cover minus half of the bar size. The proposed thickness of the foundations was 500 mm. The calculated concrete nominal cover is 50 mm, as calculated previously. As for the bar size, the intended bar size is 12 mm diameter. Take the thickness 500 minus 50 minus half of the 12 mm. That gives you 444 mm. As for the minor axis, since you have the longitudinal bar nearer to the soffit of the pad footing, the secondary bar, it will be on top of the main bars. Therefore, you need to include the diameters of the main reinforcement bar. Substitute the value 500, 50 and 1.5 times 12 mm. You get your effective depth 432 mm. What you see here, if we are using a square footing, we know that the minor axis is likely to be more critical due to two main reasons. First, your moment it will be higher. Second, your effective depth it will be smaller. Theoretically, you have to design the reinforcement bar both for the major and the minor axis. But if you are doing the manual calculations, you would like to cut short your calculation step. You may simplify your calculations by designing only for the minor axis and then apply the proposed amount of reinforcement bar also in the major axis. Since the minor axis is going to be more critical, if you propose sufficient amount of reinforcement bar in the minor axis, theoretically you don't have any issue with the major axis. Now, as far as this special is concerned, we will design for both minor and major axis. Having the design moment and the effective depth concluded, now the following step to design the amount of reinforcement bar, it will be typical. You will use the same set of equations that you use for the design of the beam and slab. First, you will need to determine the K. Use the moment 214 kilonewton meter divided by FCK, which is 30 Newton per mm square, divided by the B. Since we are talking about the minor axis, the B it will be the width in terms of the major axis, which is this, and then the effective depth to be squared. We will do the same for the major axis. Take the moment divided by FCK 30 divided by the B. Since you are talking about the major axis, the B it will be due to the minor axis, which is this one, and then the effective depth to be squared. The calculated values is here. The calculated values are less than 0.167. That means no compression rebar it will be required. That means based on the calculated moment alone here, you do not require any compression rebar. That means in the case for your peg footing, you only need to provide the reinforcement bar at the bottom side of the peg footing. No reinforcement bar is required at the top side of the peg footing. However, in the case that you foresee there may be uplifting of the peg footing, then you will need to provide the top reinforcement bar, which in this case we assume that there is no uplifting of the peg footing. That means you only need to provide the tension reinforcement bar at the bottom of the peg footing. Then we calculate the lever arm Z based on the equation here. Substitute the K value into the equations. You get the Z equals to 0.987 and 0.983 times the D. These two values are greater than 0.95D. Therefore, we will use 0.95D to calculate the Z. Use 0.95 times the effective depth, you get the Z. Same goes to the minor axis. And then, based on the Z calculated, we determine the AS required using this formula. The design moment for the major axis and the minor axis are here. Substitute into the equations divided with 0.87, FYK, which is 500, and then the Z, which was calculated previously. That gives you the AS required for the major and the minor axis here. Let's say we provide just enough amount of reinforcement bar, which in the major axis you have 9 units of H12 mm rebar, whereas in the minor axis you have 11 units of H12 mm rebar, giving you the AS provided slightly greater than the AS required. Because the AS provided is greater than the AS required, as far as the moment is concerned, the provided amount of reinforcement bar is sufficient. This, of course, you will need to check against the minimum bar area and the maximum bar area. You have two formulas to calculate the minimum bar area. One is by this formula as given in the Eurocode. Another one is given by the ratio in accordance to the concrete grade. The two requirements will give you slightly different AS minimum. You will use the larger value as your AS minimum. To calculate this, you need to first determine the FCTM. You can get the FCTM from Eurocode 2, table 3.1, which is this row. Grade 30, your FCTM is 2.9 Newton per mm square. Substitute the value into the equation. 0.26 times 2.9 divided by FYK, which is 500. Multiply the BD. Also careful with the B when you are calculating in the major and the minor axis. Since we are talking about the square footing, the B it will be the same. However, the D differs. For the major axis, the D is 444. For the minor axis, the D is 432. Then you calculate the AS mean due to the equation here. Next, you calculate the AS mean due to the recommended ratio. Grade 30 will have the minimum area of 0.15% of the effective sectional area, which is BD. Again, the D differ. As for the B, you have to refer to the relevant B here. Eventually, it gives you the AS mean. The bigger value of the two will serve as the AS mean. Compare the AS mean with your AS provided. Now, your AS provided here is less than the AS mean. Therefore, you will need to increase the amount of reinforcement bar so that it passes the AS mean. AS mean is a measure to control the crack within RC members. Let's say now we provide just enough to fulfill the requirements for the AS mean. 12 units for both axes with the bar diameters of 12 mm. That gives you your AS provided 1357, which is slightly greater than the AS mean. Now you fulfill both the AS required as well as the AS mean. Then you check the AS maximum, which is calculated on basis of the 4% of the cross-sectional area. The AC here, it will be dependent on the major and the minor axis. To calculate the AC in the major axis, we are talking about BF multiply the TF. Now, if we are referring to the minor axis, we talk about HF times TF. Since the peg footing is square, then the AS maximum it will be the same. Check the AS maximum against your AS provided. The AS provided now is less than the AS maximum. That means the AS maximum is not exceeded. In this case, you know that there is no issue with brittle failure. You know that the peg footing is not over reinforced. This is about the design of the reinforcement for the peg footing. Later we will talk about the checking for the shear resistance in our following videos. Stay tuned.